Hey everybody, this is Larry. This is me going over Q4 of the weekly contest 299. Minimum score after removals on a tree. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this very tricky problem. And I've kind of mentioned this before. So yeah, Discord is free, so come hang out, ask questions, whatever. But I would say, yeah, I would say this is a very hard problem in terms of interviews. I don't think this is in the scope of most interviews. If you're from India or China and you're talking about online assessments, I apologize. So maybe it's not accurate there, maybe. But otherwise, for the most part, this is very hard. It's definitely a competitive E problem and not so much an interview E problem, if you ask me. But who knows, right? This is as of the year 2022, so if I'm wrong in the future, don't hold me to it. Things are getting harder, it seems like, but I also could be wrong on that one. But anyway, so yeah, so the key point about this one is the first thing you should know is look at the constraints. The constraint is n is equal to 1,000. What does that mean? That means that n squared is going to be fast enough. So that's basically my idea. And one thing that at least just me analyzing is myself anyway, is that I probably should have done this in C++ because I definitely had some doubts on Python. I mean, 1 million times some constant should be fast enough, but Leetcode has been doing kind of a poor job lately ensuring that, I always just have doubts in general about it. And as a result, like if I was just like, for example, maybe it is still O of n squared, but if I added one extra operation that makes it go like 20% slower, maybe that makes a TLE, right? Even though the complexity is the same. Where in C++, you have to like go really far out in terms of inefficiencies, constant level inefficiencies to get TLE. So maybe I should have done it that way because I kind of was slowing myself down to kind of figure out if I could do a little bit better. But if I had just used another language, maybe I didn't have to. But anyway, so yeah, noticing that, well, two things, right? One is that it's a tree. And second is that n is less than 1,000. That means that there are a couple of things you can do, right? If we need to remove two edges, then you could actually enumerate both those edges, right? And if you're able to do all the calculation in O1. So that's basically the idea for this problem. I'm gonna pull up some drawing real quick. And then the idea here is, I was gonna copy some of these, but let me actually just draw some trees for you real quick. But for example, the idea here is that, okay, remember, this is an unrooted tree, but we can root them in any node. It doesn't really matter. I always root by 0 in those cases. But yeah, so let's just say you have some node, right? You have some tree, and I'm just drawing it out relatively, right? And then, so there are two things that you can do, right? One thing with respect to this problem, and let's skip the XOR part for now and focus on getting the components, right? So what do I mean by that? So let's say we're using a regular sum. Let's say we're ignoring XOR for now, right? Just because I think it's a little bit easier to understand, and then we could go over the translation to XOR in a second. But here, let's say you want to solve. I think this is a problem that is maybe even Q2 level-ish, something that you certainly should know for an interview, which is getting the sum of all the subnodes, right? So that's pretty straightforward, I hope. And what I mean by that is that, this node, we store the node value, and then on this node, we store the sum of the subtree, right? And then on this node, we store the sum of all the subtrees, right? So let's say we have all this, right? Okay, we gotcha. Okay, so then now, in order to brute force, okay, so let's say we built out this thing with the sum, right? Well, then and still we're talking about regular addition for now. So how do you get, two, let's say we cut off just randomly two edges, right? Say this one and maybe let's say this one, right? Well, what does that mean? That means that we're effectively looking at this subtree and this subtree as two of the components, and as well as, you know, the remaining portion, right, of the subtree. So basically, these are the three components we're looking at when we're looking at these two trees, right? And they're really they're kind of two cases that you have to consider, right? One is what we just did now, which is that we have three subcomponents kind of looking like this, where the root is one component, and then you just have to look at, yeah, right? And I think one thing, and let me do the other thing first, actually. So that's basically one case that you can do. The other example that of a thing that you can do is that, like, let's say you cut off this edge and you cut off this edge. Well, what do I mean by that? Why is it different? Well, that means that this is the subtree, and technically this is the subtree, obviously. But you know, you have to do some math to kind of, you know, remove this part, right? And then you have this other remaining thing. So that's basically the only three example, right? Or sorry, the only two cases. Basically, you have, you know, you have a node 0 at the, let me actually, okay. Give me a second. So basically, these are the two things, right? Two ideas, the two examples, the two cases that we have to consider. Okay. Let's go back a second, right? So let's say we cut off this edge. What does that mean? When we cut this edge, means that this node is the root of the subtree, right? And when we cut off this edge, we mean that this node is the root of the subtree, right? So I want that to be clear, so that basically what I'm saying now is that we're converting between removing an edge and saying we want the, I hope this is on the board. Okay. I had a minor worry that I'm like not showing you what I drew, which is then waste of time. But yeah, so I'm just doing the conversion from removing an edge to, say, counting the sum of a subtree, right? Okay, so now that we have that, another thing that we can think about now then is now we can iterate every possible nodes, right, as the trees. And then here again, we only have two cases, right? Let's say we have so one of the root is always going to be 0, just because you can arbitrarily choose it, right? It's just the root of the remainder stuff, right? And I kind of want to erase this because that arrow is terrible. Yeah, right. Actually, let's use this one because I have an X still here. So there are three nodes, right? In this case, let's say you have a node of I, you have, say, I and J. Did I say I? I meant 0. So here you have a pair of 0, I, and J, right? And this is going to be for every node, and there are only two cases that we have to consider. One is, well, 0 is always going to be a parent of I and J, right? In some non-direct way. So this is for all cases. So there are only two cases. One is that whether I is the parent of J, and of course, without loss of generality, you could say J is a parent of I. It's a different case, but you know what I mean. And then the other one is that I is not equal to the parent of J, right? And for that, let's say, you know, for a very easy example, say this is I, right? And then that means that I is not equal to J, right? So yeah, so that's basically the idea. And now given this idea, what are we doing, right? So like I said, with the green eye, so we know the sum of all the nodes because the sum of all the nodes is located here. Let me actually use a different color real quick. No, green is fine. So sum of the node here. So then now we have the node here, right? And the nodes here. So then now we have, let's say, S of I for sum of I, S of J for sum of J. That's really, and sum of S of 0 for sum of 0. Well, then now you have your three scores are S of 0. Well, S of 0 is the sum of all the tree, right? So the sum of the nodes that are not in I and J is just S of 0 minus S of I minus S of J, right? And then the second score obviously is S of I, and then the third score is S of J. Okay, so that's one example. This is one edge case, right? Of what we what the geez, of what we're doing, right? Okay, well, and then the other case is, as we said before, I'm going to change back to red real quick. Right, we have the s of, this is the s of I in the red color one. So then now we have, well, we have three nodes, right? One is s of 0 minus s of I. We don't have to minus s of j because s of j is already included in s of I. And then the second node is s of I minus s of j. And then the third one is s of j, right? And that's basically the two cases we have to consider depending on whether they're parents. So that's basically the entire part of it, assuming that we have total instead of XOR, right? Let me now be able to turn it off. Hopefully this was good visualization. And then now converting that to XOR is just that instead of using XOR subtraction, we use XOR. Oh, sorry. Instead of using arithmetic subtraction, we use XOR subtraction, which is actually just XOR. So that's basically the idea. And then here, with that point in mind, we'll go over the code. So here we just construct the edge list. This is relatively standard. If you are confused about that, do work on graph problems on Leetcode. I'm not going to go over that in this video just because this is a very long video. So here is basically values of I contains the XOR sum of all of subtree under I, right? That's basically what this does. And of course, this is a regular tree problem, so definitely get familiar with that as well. I'm not gonna go over it, except for that, we just sum all the, we do an XOR sum of all the subtrees and including the current node. That's what this does. And then we cache it in rows, right? And here I actually did another thing of parent sub I contains, I actually messed up on the variable names, but contain all the children of subtree, or not children, but descendants. Did I spell it right? I don't know if I spelled that correctly, but of I, right? Of node I. That's basically what this does. And I actually did this in a okay, let's actually go over the complexity of this real quick. This is just a regular depth first search, regular subtree sum. So this is actually going to be O of n in time in total. And I used the O of n because this is a tree, so the O of h is the same as O of n, which is the number of nodes. Here, however, it is not O of n because we call this O of n times. Each of the time takes O of n because of the set not intersection, set union. This is the set union that we have, and because in theory we could keep on bubbling up, that is going to be O of n. So for each time, so this is actually O of n square time, right? And O of n square space technically, but and this can be improved with binary lifting as well. Trading time for pre-processing time for query time, because now what this does is that because we did an O of n squared time, later we can do this in O of 1 lookup, where if we did binary lifting, it would be log n lookup. I don't know how we feel about it, but that's basically my logic. And here we construct or this as well. This is just pre-processing on the set entry. Yeah. And then this is basically the brute force thing that we talked about, right? Am I showing the correct data? Okay. Yeah, basically. And so I did get a wrong answer, and it's actually a very painful wrong answer, because I think it would have put me on maybe 25th or 26th. Would have been maybe 27, say. But that, well, I also spent a minute debugging. So let's say top 25, but because of this debugging, this issue, this bug, I went to 45th. What was it you say? I basically started from 0 instead of 1 here, and I got that wrong because then now you're doing the 0 node twice as one of the possibilities. Silly Larry. But yeah, but basically this is saying that we have the tuple that we talked about, right? We have 0, I, and j. And then we just basically go over all the edge cases of, okay, if I is j's parent, if j is i's parent, and then this is no I and j doesn't mix, right? And that's basically the idea, is that, okay, if I is j's parent, then route sub I already contains j, so you only do it this way. And this is, you know, this A, B, and C matching is what we talked about in the graph, or what we drew out, right? It's just that now we're using XOR subtraction instead of arithmetic subtraction. Same thing here, but you know, the other way with I and j. And then here, if it doesn't mix, then yeah, you know, we already did the visualization. Hopefully this makes sense. And then finally, we take the max of it, and then we subtract from the min of it, and then we take the min. So this is the score, and then we take the min of that score and put in best. And that's pretty much it. And you can see from this complexity that this is n square, and everything here is all of 1-ish. So yeah, I feel a little bit sad that I got a 5-minute penalty because I started from 0 instead of 1. I kind of was thinking about it and then I forgot about it. So very sloppy, but I'm happy that I got it in general, because these kind of tree problems I wouldn't say I struggle with, but I definitely am not as practiced. And this one, I would say that I really like this as a competitive problem. As an interview problem, wouldn't done so much. So yeah. Again, I'm just going to show the code again before we go. So this is n squared, just to be clear, and or one space. So everything is going to be O of n squared time and O of n squared space, because the O of n squared space is on the parents checking to do it quickly. Otherwise, this is actually much less space. Again, you could do stuff like binary lifting, but to reduce the space, but I think you pay it in cost of time, so I didn't want to do that. Cool. Yeah, so let me just show you the code real quick. Again, just for the people who wants to copy it. Yeah, so this is the XOR sum. You could probably put it together, but this is the descending code for depth first search, and then here is just the brute force and just making sure we get the cases right. Cool. That's pretty much all I have for this one. Let me know what you think. Yeah, hit the like button, hit the subscribe button, and you could watch me solve it live during the contest now. Okay. Was worried that I had a typo somewhere. Okay. Okay, you have a connected tree. You have edges. You have y and edges. We move 2 edges to fill. Okay. Get x of order with each of the 3 respectively. Okay. I get the idea. Am I doing okay? I guess it's not 10 minutes yet. Shouldn't worry about that though. I think that's a silly move, Larry. Okay. So what we want is an XOR of all those things. How do I think about this? Well, how do we think about, I mean, n is 1000, so n squared is good enough, so that means that we should be able to do it in a good way, right? So, okay, given one XOR, we have XOR of the subtree, okay, right? And then, okay, XOR is just XOR sum of all the values, okay, fine. Okay, I think I did get that idea. Can't help it. Are they done yet? Oh, 55, huh? You were very fast. 3 minutes. Okay. I thought I was faster a bit. I still don't know how to do this yet, but I do have an idea of getting about a subtree, and an XOR is just all of them. So, okay. Let's just say if so the current 0 0 and then return current, and then we have for e in e sub node. If we is not p, then code re node, and also current is num sub node. Okay, so this will give me the entire tree of XOR. And now to figure out how to do it, right? The edges in a good way. We can brute force the edges, maybe if we can do all of one, but let's actually quickly start it. Okay. Okay, so for each node, what do we want to do? So what do we do? We want to minimize the score. Okay, I actually missed that, but how do we do it? Do we do brute force? Each node n square is far too slow. So we have to do something slicker than that. Wow, 3 people got it already. People are really smart. How do we do this tree thing? So given a node, we have something like this, and then we want to get this and this, but how do you do it? Right? Well, there are two things, right? One is, okay, so we want to get the XOR of node of 0. So 0 is always one of the nodes, and then it's just brute force on the other two, maybe? Okay. Maybe that's true. I don't know. Okay. Sure, this is true. Okay, but then we have to get, in order for this to work, what we want to do is figure out what is the parent thing, right? Well, 0 is going to be 1, but then the other one may have. Okay, so. Okay, I think I have the idea, but I'm trying to figure out how to do, I'll say, in very good time. Which there are ways to do it, but I'm trying to think if there's a better way. Other than some like binary lifting. Well, so each of these would do at least worth 1,000. Okay, maybe that's fine. Okay, actually I think I get it. Okay, because this is 1,000, that should be fine. Okay. So we want to look. Okay, fine. Basically, what we want. I get the idea of implementation is hard. Okay. I do wonder if this is gonna time out though, to be honest. Should be okay, but who knows anymore. Oh. Because this should be on square, but okay, so then I'll go to okay, and now we have the score is the minimum delta, right? So okay. Oops. It's hard to scroll down sometimes. Let's see. Now we want root to be 0, I, and j. So okay, so that means that we have maybe this doesn't. Just one real quick. Okay, doesn't work. Okay, if j is in, this should actually occur sometimes though. So that's actually very bad. Maybe. Oh, this should be containing node, and then here, if I is equal to j, will continue. Okay, so that's good. Okay, if also pause up. So this means that I is j's parent. Then score is equal to okay, raw sub 0. That's what I maybe this is should be this. So this is the score of the 0. And and C is equal to minus of J, and then best is equal to min best of max ABC minus min of ABC, which is actually pretty yucky, but let's try real quick. 9 and 0. This gives the right answer, but it's not sufficient. Else if I isn't positive J, then I'm really worried about timeout though, to be honest. Maybe I should have done it in C++, but so J is ice parent, okay. And then otherwise, okay. I don't know if this is going to time out, but I hope this is right. We'll see. Maybe it times. Oh, wrong answer, huh? My math is bad, I suppose. A lot of people got it now, but okay. So you have 0, 3, 3, 1, 2, 3, and then you have 9, 14, 2, and 1, right? My output is 6, but why is that? Oh, I guess this is no longer true, but that doesn't change anything. Why do I have 6? Whew. Well, I guess this is fine. This is also actually just good in general. So 6 is here, but why 0 and oh, I messed up because I chose 0 as one of the roots. I think I needed something like this. Okay, that is a silly mistake. And then now we'll see if I get a time limit. That should have been obvious, but still a little sloppy today. Okay, cool. Yeah, sloppy on the Q sloppy on the wrong answer. But I feel like, I mean, wow, numbers. Good job, Josh. Yeah, thanks for watching. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. Stay good, stay healthy, to good mental health. I'll see you later and take care. Bye bye.